Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Today's video is less related to game engine programming and more about creating utility functions that we need in order to organize the data within the engine. Of course, it's hard to go about without good containers, and as we have seen in the previous episodes, we are desperately in need of having a free list container that can help us host the data in a nice and tidy buffer. So today I'm going to quickly explain what the free list is and then proceed to implement one. A free list is a relatively simple container which consists of a buffer that is formatted in slots big enough to contain an item of type T. Every time we add an item, the buffer grows to make room for more items. However, when we remove an item, instead of shrinking the buffer, the index of the removed slot is put in a member variable that I call nextFreeIndex. When there are no removed slots yet, the value of nextFreeIndex is an invalid ID. When more items are removed, we use the first 4 bytes of each slot that was previously removed to record the index of the next slot that was removed. In a way, we are creating a linked list of available slots, and each time a slot is reused, we update the value of nextFreeIndex to point to the next available slot that we can use. The last available slot points to an invalid ID again, so we can determine when there are no slots left to be reused and we need to grow the buffer. Now we are ready to implement the free list. Let's add a header file here that will contain the free list template class. As always, include common headers, and I'll also include this header file in utilities, so every file that includes common headers will be able to use the free list as well. Here's a template class because we need to be able to use it for different data types. And this free list is basically a buffer. And for that underlying buffer, I'm just going to use a vector. And as I explained before, we are going to store the available slots in this buffer in the slots themselves. That's the idea behind the free list. And because I'm going to use 32-bit indices, that means that the size of a slot can't be smaller than 32 bits. And therefore, I'm going to put a static assert here that will check if that condition is true. So the compilation would fail if we tried to use a free list with a data type of size less than 4 bytes. Next, I'm going to add 2 constructors, one of which is just a default constructor. And the next one accepts a number that we can use to reserve some memory in advance. Here I'll add another member variable to remember how many slots are in use. And in a destructor of this class, I will check that the size of this free list is 0, and that means that all the slots have been freed before destructing this free list. We also need a variable that will store the index to the next available slot in the free list. Then, when we want to add an item in this free list, we can check whether there is a slot available already. And if so, we can reuse that slot. And if there are no slots available, we need to allocate a new one. When we add an item, we will return its index in this array. If the value in nextFreeIndex equals the invalid ID, that means that there are no free slots available and we need to allocate a new one. And I can do that by simply calling arrays emplaceBack. And of course, we need to know what to put in this array. So if we look at the emplaceBack function defined in vector, you can see that it takes an arbitrary number of values, and those are the constructor parameters that are used to construct a new instance of this T. And what I'd like to do in this add function is just to accept the same parameters and forward them to mPlaceBack function so that vector can construct a new instance of t. But before this, we also need to determine the index, and that's just the position of the new item in the array. So this is what we do when there are no available slots. But if there are already slots available that have been used and removed, we can reuse those. So that's what we do here. The first 4 bytes of an available slot contain the index to the next available slot. And this is how we read that information into the next free index. This might as well be the same value as invalid ID. That means that there is no available slot. And in that case, the next time we want to add an item, we will need to allocate new memory. And also notice that I'm using the address of function, because if the type that we are using in this class, which is t, if that type overrides the address operator, which is normally this one, if that's the case, that means that using the address operator won't give us the address of this item anymore. And that's why we use the address of function. Here I'm using the placement new operator to construct an instance of t using the constructor parameters that it might have at this address. So we have room at this address and it just constructs an instance of t in there. And now that we are done constructing an instance of t, we need to increase the size of the free list and return the ID, which is the index of this item. Then we also have the remove function, which will remove an item from the free list. Before removing an item, we need to destruct it by calling its destructor. And then we write the index of the next free slot in the first 4 bytes of this location. And here we put the current index of this item that we just freed into the next free index. And decrease the size of free list. Now here I'd like to do a couple of checks in add function and in remove function. When we are trying to add an item in the free list and we are going to reuse one of the slots, I would like to check whether the ID is valid that we get from next free index, and also assert that this slot was indeed removed before. And to determine that, we need to put some extra information in such a slot. And of course, we do the assertions only in debug build and not in the release build. And the way I want to put the extra information in a slot is by filling it with a random value in all its bytes. So here, when we remove an item, I'll have a debug operation. By the way, if we look at the definition of this debug operation, you see that it's defined after including the utilities. And therefore, when we are going to use these functions, it says that debug of macro is not defined. So we need to put this before this part. And this is not necessary. So here I fill every byte of this item with a random value of cc. You can choose any value. I chose this one because it's also used by Visual Studio Debugger to fill in uninitialized sections of memory, I think. Let's look it up. So here, if this is right, we have the table of debug values that are filled in memory by Microsoft compilers. And you can see here that cc value is for uninitialized memory. And this is also the value that I'm going to use. Now that we filled in the entire slot with this value and used the first 4 bytes to put the index to the next free slot, we can add a function here that we can use to check if after the first 4 bytes, the rest of the values are all cc. Obviously, we can't do this when the size of the type that we are using equals the size of a U32, because it will be all used up for only the index, and therefore I can exclude that case from our check here. I'm going to use if const expr. And if that's not the case, that means that this code block will be excluded by the compiler. Here I get the address of the item and convert it to a pointer to an array of bytes, and then skip the first 4 bytes and compare the rest with this value. And while that's true and I is less than the size of our type, we advance to compare the rest of the bytes. And when we reach the end of the slot, the value of I should be the size of t. And if that's true, then this slot was already removed. And if our data happens to only be 4 bytes, then we just return true because we can't check other bytes. Then here, when we remove such an item, we can check if it wasn't already removed. And when we are reusing a slot, we need to check if it was already removed. Of course, we also need to be able to access the items in the free list. So I'm going to write the bracket operator that we normally use to access arrays. And for good measure, we define the const version and the non-const version of it. And finally, I'll add 3 more functions to get the size, the capacity, and whether the free list is empty or not. And this is all we need to do to have a free list container, and we are now ready to use it. I'm getting a bunch of errors, so let's see what's going on here. Of course, I need to specify type for our function parameter here. And spell things correctly as well. Now, the first use case that I can think of is here in platform CPP, where I already made a comment in the past here that we'll be using free list container, and this part can be removed. So let's see if I was right and remove this part. And of course, we need to replace the vector with the free list. And now all we have to do is to, instead of calling these functions, call Windows add and remove functions. I also forgot to give the already removed function an ID here. And that's all it takes to use our free list. Just call these 2 functions and it works. Now we have these windows. I forgot to limit the frame rate here again. So let's close these. Check if we have any memories leaked. That's not the case, so that's all good. Go back to the test renderer and enable this sleep for 10 milliseconds so we don't fry our graphics card or anything by accident. So this looks all good, but there is something that's not correct. You might have already guessed it, but let me explain. This window information, which we put in the free list, is a trivial data type. And that means that it doesn't have a user-defined constructor, a destructor, or any move constructors and move assignment operators and copy constructor and copy assignment operators. And if you want to use this free list with a data type that's non-trivial, that means that we at least have something that's like a destructor here. So if we have a destructor like this that checks if is full screen, Boolean here is false, then when I run this program and shut it down again, we will get an error. Here this assertion fails because when this free list instance itself is getting destructed, the destructor of vector will also free up all the memory, and that's where it will call the destructors again. And because we filled this value in all the slots, that means that all items now contain some invalid value. And when their destructor is trying to clean up, that means that it could be dealing with some invalid data. So what I need to do is to make the vector class here not to call the destructors of its items when it is getting destructed. And with the vector implementation of the standard template library, that's not possible. And therefore, I need to write my own implementation of vector. And therefore I need to write my own implementation of vector, which takes an extra argument which I can use to tell it not to destruct the items. Okay, let's add a new file that contains a template class for the vector. Here I define a new vector class, and it takes a template parameter of type t. And we also give it a Boolean optional template parameter, which has the default value of true, so the vector will destruct the items when it is destructed itself, or we are removing items. In general, it will just not destruct anything if we set this template parameter to false. That's the purpose of the parameter. Now the first thing that I'll write here is a couple of constructors. And the functions and constructors that I am going to add here are roughly in parallel with the standard template libraries vector. So we don't have to change anything in the code to use this vector. Here, unlike what I use most of the time, which is AU32, I'm using a 64-bit value here for this parameter, and that's because the standard template library vector also uses a 64-bit value. So this one allocates memory for this number of items and also uses the item's default constructor to initialize each item in the array. And sometimes we want to initialize all the items with a particular value, and therefore we can use this one. Next, I'm going to write the copy constructor, copy assignment operator, move constructor, and the move assignment operator. For the move constructor, we need to know what members we have, so I'm going to add those here. In this vector, we have a buffer of type t, and we allocate a memory that's as big as the capacity, and the size signifies what portion of the capacity has been used to put items in. And when we are writing the move constructor, we need to assign these member variables from the other instance that we are trying to move into this one. When we move everything from the other instance to this one, we need to reset the other instance to its initial value. And therefore, we need to write a reset function here. And what it does is basically just set these three variables to their initial value again. So this one copies all the items from the other instance to this one, and the move constructor will move everything over and leave the original vector empty. Notice that here in the copy constructor, I'm using the copy assignment operator, so we need to still write that one. Here I assert that this vector is not being assigned to itself. In general, it's okay, but I put an assert here because that could be not the intention of the programmer, so we assert for that. So if the instance that we are copying is not the same as this instance, then we can clear everything that's already in here, then reserve enough room to hold the items from the other instance, and then copy everything from there to this vector, and then check that the size of this vector is the same as the size of the other vector. Then we also need to write the move assignment operator. Here again, we check that the vector that we are trying to move from is not the same as this vector. And if that's not the case, we destroy everything that is already in here and then move all items from the other vector to this one. And the last function in this bunch that we need to write is a destructor. And that's basically the rule of 5 or 6 or whatever. That says that every time you have to write the move and copy constructors and move and copy operators, if you have to write any of those, then you need to implement all of them. So all the constructors and all the assignment operators and also the destructor. So let's do that here. Now, as you already noticed, we have a bunch of function calls here for functions that we still need to write. So let's try and write these functions. Again, this function is really simple. It moves the internal data from the other vector and resets that vector. Then we can go ahead and implement the destroy function, which destroys all the items in the vector. Here we have the destroy function, and it will clear the array first and then set its capacity to 0 and free the data buffer if it was already allocated. And before doing that, I'd also like to check if there is something to destroy anyway by asserting that. Here is a bit of a weird assertion, which is a lambda expression. And it's just a function call that checks the fact that if there is some value in a capacity, then we must have a valid pointer for data, otherwise that wouldn't make any sense. And if there isn't a value for capacity, so the capacity is 0, that means that there shouldn't have been an allocation for data buffer as well. And with this lambda expression, we check this relationship between the capacity and data. And then we can try and implement clear function. Here is where the destruct template argument comes into play. And again, I used here an if const expert. And if that's true, then we destruct the entire range in the array that spans from 0 to the last element and set the size to 0. Then we have destruct range that we have to implement. Here we check that this function is called when destruct is true. Otherwise, this function call would never happen. And also check that first and last are within the ranges of the array. And also that the first item that we want to remove is before the last item that we want to remove. Then if there is a data buffer, then we go through all the items from first to the last item and call their destructor. And this is where I'd like to stop for today. Next time, I promise I'm going to finish implementing the vector class and put everything together so we can use it in the free list and have it also interchangeable with the standard template libraries vector. I hope you found this video useful and that I earned your subscription. Thank you for joining me, and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!